Hello everyone! In this video, I'm going to explain the logic behind the definition of a limit and also how to use it in proofs for your class. So we're going to use an example problem here to explain the logic behind the definition of a limit. So the question is to prove that the limit as x goes to 2 of f of x equals 4 for the function f of x is x squared when x is not equal to 2, but is x when x is equal to 2. So down here we have a graph sketched out of this function, and we can see that it looks like x squared is y, f of x is x squared, except at the point x equals 2 here we have a hole, where at that point f of x equals x, which is 2. And we see here that for some arbitrary point on the curve, some point xy, the coordinates are x and f of x, which is y. And we'll call this distance from x to 2, this distance, which is the absolute value of x minus 2, we'll call that the gap, okay? The gap from x to 2. And that gap is going to go to 0. And then looking up here, the distance from f of x to L, the limit, which is the absolute value of f of x minus L. We'll call that the error. That is telling us how far off are we from the limit. The output of our function, how far off is that output from the limit, okay? And then we're going to relate the gap to the error and show that as the gap between x and 2 goes to 0, so also does the error between f of x and the limit go to 0, which will prove what we set out to prove in the first place. Okay, so now we're going to find the relationship between the error and the gap so that we can show that as the gap goes to 0, the error also goes to 0. So the error is equal to absolute value of f of x minus the limit, which, substituting in, f of x equals x squared, and the limit is 4. And then continuing with our algebraic simplification, we have absolute value of x minus 2 times x plus 2, which is also equal to the absolute value of x minus 2 times the absolute value of x plus 2. A little simplification here. As we get really close, as x gets really close to 2, x is going to be greater than 1 and less than 3, right? So this absolute value of x plus 2 term will be less than 5 when we're really close to 2, because 3 plus 2 is 5, okay? So that means here we can substitute in less than or equal to, right? It's all, the error is less than or equal to x minus 2 times 5. Okay, now see here, we have absolute value of x minus 2. That's the gap. So what we just did is we showed that the error is less than or equal to the gap times 5. Okay? That means that as the gap, if the gap is, say, 0.5, then the error could be 2.5. Or if the gap is 0.1, then the error is no more than 0.5. And if we reduce the gap going all the way down towards 0, say it's 0.001, then the error is no more, the distance from the limit here is no more than 0.005, which then as the gap goes to 0, the error goes to 0. So now, how do you do this in terms of epsilon and delta? Well, going back to the definition of a limit, the limit as x goes to c of f of x equals L, or the limit of as x goes to c of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon, and the absolute value of x minus c is less than delta. Now, remember these terms? This term is our error, and this term is our gap. So all you have to do is basically say that the error is less than some epsilon, and the gap is less than some delta, and relate epsilon to delta. You know, there's some relationship to each other, and show that as delta goes to 0, epsilon also goes to 0. And so for your professor, you would start by just writing f of x minus L equals absolute value of x squared minus 4, and continue on to what we did before. Substitute in for x plus 2, right? When x is really close to 2, then this value here will be less than or equal to absolute value of x minus 2 times 5. Okay? And so now we see here, now we'll say this is all less than epsilon, right? The error is less than epsilon. So we have x, absolute value of x minus 2 times 5, all being less than epsilon. We also have x minus c, in this case c is 2, absolute value of x minus 2 is less than delta. Okay? So then, since epsilon is 5 times the absolute value of x minus 2, and delta is the absolute value of x minus 2, all we need to do is make sure that our epsilon is 5 times as large as our delta, and we're good. Right? Going back to the graph, if our delta is yay big, encompassing our gap, we just need to make sure our epsilon is 5 times larger than that. And as delta goes down to 0, epsilon will also go to 0. And so here we would just say let 5 delta equal epsilon. And that was the proof right there. This here is the proof.